degree wedge, what would happen? Well, it would tilt 10 degrees. Let's see what happens to the real foot when you place it on a 10 degree wedge. 10 degree wedge, identical. It doesn't change at all. In fact, Craig Payne did a study where he took various size wedges on people with everted heels and found that in 50%, half of the cases, calcaneal eversion increased. Why is that? Theorem 3, rear foot fall through. There's the theorem of compensation right there, happening. Here he is with a wedge and without a wedge. See any difference in the height of the longitudinal arch by wedging? No, I don't. How about here? Any difference? Nope. I get from podiatrists to go, but you didn't incorporate it into a full Russian device, a neutral orthotic. I said, well, he had one. He had one with 6 degrees of rear foot posting. Let's take a look. Here he is without the orthotic and standing on the 6 degree post. The curvature of the Achilles without an orthotic, with an orthotic. Absolutely identical. Now let's try something different. Let's actually support the medial longitudinal arch. What just happened? We changed the inclination angle of the first metatarsal from 18 degrees to 26 degrees. Huge change. Which, by the way, is in agreement with Theorem 5, which states when the ideal foot is fully loaded, neutral calcaneal stance will equal relaxed calcaneal stance. That would be the ideal foot. In this foot, you've just accomplished that. Look what happened to the heel. This is actually Theorem 2, rear foot perpendicularity. That the rear foot will attempt to compensate to perpendicular. So what happens when you support the medial longitudinal arch? When you prevent further forefoot compensation, the rear foot stops at perpendicular. What happens when you raise the medial longitudinal arch? The knees go from internally rotated close together to separated on the sagittal plane. Here's the Russian posted orthosis, and here is the medial longitudinal arch supported orthosis. Do you see a difference between them? Look at the difference in the calcaneal bisection. Rectus everted. This is a good orthotic. It's in full contact with the foot. But when we send this cast to various labs around the country, we get an orthotic that's got a space. This was the best one. This is what most of them look like. You could stick 4 fingers in there. You could drive a truck between your foot and your orthotic. You could smuggle diamonds into the country between your foot and your orthotic. That's wrong. Orthotics should actually touch the foot. Third reason why rear foot posting won't work. Newtonian physics. All of Newtonian physics can be derived from this simple formula. F equals ma. Force is mass times acceleration. What is acceleration? Acceleration is a change in velocity in a unit of time. 0 to 60 miles an hour in 5 seconds. What's velocity? A change in position in a unit of time. So force is inversely proportional to the square of time. Let me translate that to English. If you want to do some work and you have a little bit of force, it'll take you a long time. Okay? You want to dig the Grand Canyon? You could do it with the gentle force of the Colorado River in 10 million years. You could also do it in a minute with an earthquake. Huge force, little time. How much time do we have in 3-mile-an-hour gait from heel strike to full pronation? 0.07 seconds. There's simply not enough time for a heel post itself to apply an adequate force to control 3 times body weight in this amount of time. So what am I going to do now? Give you an orthotic that creates time? Yes. Is trick. If you heel strike here, that is, you prepare the foot to hit the ground, with the anterior facet level, you've created a time delay. If you heel strike here, with the anterior facet tilted, you're driven into early rapid deep pronation. So we create a time delay, which is enough to lift the bottom graft to the normal graft. Remember, disease, deformity, pain, injury, they occur at the end of pronation, in the pathologic zone. So where would you apply your corrective force if you wanted to stop pronation or control pronation? Here's what I was taught. Take a small wedge and put it under the medial side of the calcaneus. Will that stop you from pronating? You'll roll right over it. It will cause a slight resistance to pronation, maybe enough to get you from just above the threshold of tissue stress and symptomatology to just below it. That's about what it will do. Wouldn't it be better if we took a great big wedge and placed it right in the sagittal plane? Not made of wood. Okay? That's too rigid. You couldn't tolerate it. But if you take a great big wedge and put it in the sagittal plane, you will block the forward roll of the calcaneus. That great big wedge is what? The medial longitudinal arch of the orthosis. And this is what hit me when I was reading the theorems. The foot will continue to collapse until it is directly supported by something. Something stops it. It could be the ligaments. It could be the muscles. It could be the ground. But it also could be the orthotic. This is directly in agreement with Theorem 3, rear foot fall through. The foot will continue to fall through until something stops it. What am I doing? I'm installing something to stop it. Does that make sense? Let me add one more physics property. You cannot apply a force through thin air. In order to apply a force, you have to actually touch the foot. Okay? Why did previous attempts at raising the longitudinal arch fail? Because they were taking you from the pathologic zone up to what? The dysfunctional zone, the area of high repetitive impact. So when they raised it to the dysfunctional zone, they got sent back as a warranty. The lab said, whoa, this is costing us money. Let's fill it back in. And they retreated back to lowering the arch. The second reason was they didn't know the answer to this question. Should a foot orthotic be rigid or flexible? What's the right answer? The answer is yes. The question is misstated. The correct question is, if I take a curved piece of material, I place it on a flat surface, how much vertical force should that material exert on the human body? That I can answer. Newton's third law. For every action, there's an equal and opposite reaction. You want me to tell you how much force the orthotics should apply? How about you tell me how much force you're going to apply? What causes the downward force of the human body? First and foremost is donuts. It's body weight. That's easy to measure. You can weigh somebody. Secondly, how flexible are you? If you're extremely flexible, the ligaments are not helping. Therefore, the orthotic has to do more work, has to apply a greater force. If you're very rigid, you're already held in place. The orthotic has to apply less force.